So now we want to use Gauss's law to compute electric field due to a charge on a wire of infinite length and constant charge per unit length. So say we are given lambda is the charge per unit length. And the total charge for this length L. So wire is of infinite length, so we are just picking a small length L out of the infinite length of the wire, and on this small length L the charge you says Q is given as lambda times L. Now we know the formula for the flux. Flux is given as surface integral of E vector dot ds vector. Now by Gauss's law, this is equal to Q over E0. So this is equal to lambda L over E0. So we will explain later why we can use Gauss's law. So the first condition is satisfied because we are assuming it is constant charge per unit length. And second condition, we will show that E vector and ds vector have angle 0 between them. Now E vector dot ds vector would be integral of E ds cos theta. So we will show this cos theta is 1 since theta is 0. So let us see why theta is 0. So you see the electric field is generated by the wire. So electric field is going to come out of the wire. And you can also take a small surface area on this imaginary cylinder which we have made. So I'm just going to take another small surface area just around where the electric field is passing. And to that surface area you associate ds vector which is perpendicular to the surface. So to ds you associate ds vector, and you can clearly see that electric field and ds vector have angle 0 between them. Now on the left side again the electric field is going out of the cylinder precisely because the wire is in the center and it is positively charged. Again you can see the electric field and the surface vector have 0 degrees between them. So this just reduces to E ds. Now electric field does not depend upon the area of the cylinder we have chosen. So this becomes E times the surface area of the cylinder, and surface area of the cylinder is 2 pi RL. Now you equate 1 and 2. So you get E times 2 pi R times L. This is equal to lambda L over E0. And from here you cancel out L, and this will give you the electric field. So electric field is lambda over 2 pi R epsilon 0. So you can also write this in terms of our constant K. So where K is 1 over 4 pi E0. So this becomes 2K lambda over R. So we have been able to use Gauss's law to compute electric field on a wire of infinite length because the charge was uniformly distributed and the electric field and the area vector make an angle of 0 degrees. And notice this R which we have in the denominator. So this R is the distance from the wire. So notice that this R came from the surface area of the cylinder which depends upon the radius. So obviously as you go away from the wire the electric field reduces. Now we come to the second problem. We want to compute electric field due to an infinite plane of positive charge with uniform charge density. So the plate is given now in red. So it is a positively charged plate. So flux by Gauss's law is given as Q over E0. So what is this charge Q? Q is charge density times surface area. So say charge density is sigma, surface area is S. So let us see if the Gauss's law is satisfied to compute the electric field. So notice that again ds vector and E vector are both parallel to each other. So angle between surface vector and the field vector is 0. Notice how the field vector is coming out of the positively charged plates. So electric field vector always comes out of positive charge. So the flux is given as E vector dot ds vector. So you have to find total E vector. So first we focus on the left side and then on the right side. So this is the left side of the positively charged plate and this is the right side of the positively charged plate. So both sides are having flux. So theta is 0 for both the cases. So cos theta is 1. So this becomes 2E ds or 2Es. So now we put 1 equals to 2. So you get 2Es is equal to sigma s over epsilon 0. So s cancels out. This implies E is equal to sigma over 2 epsilon 0. So notice that in the case of cylinder we computed the entire surface area, and in this case also we could have just taken the entire surface area. So the entire surface area again would have been 2s, surface area of left side plus surface area of right side, and we could have just computed again the same electric field E equals to sigma over 2 epsilon 0.